Hello, welcome. In this part, we will talk about the mathematical induction. Mathematical induction is a mathematical proof technique. It is essentially used to prove that a statement holds for every natural number, or for every natural number after some fixed natural number. Before we begin the discussion of mathematical induction, let's start the discussion with the well-ordering principle. This principle says every non-empty subset of the natural numbers has the smallest element. The principle can be restated as follows. If A is a subset of a set of natural numbers, and if A is non-empty, then there exists some element in A such that n is smaller than k for all k in A. For example, consider the set A, the subset of the set of natural numbers. Then we see that there exists a 5 which is smaller than x for all x in A. In other words, 5 is the smallest element in this set. So every non-empty subset of the set of natural numbers contains the smallest element in that set. Theorem. Principle of mathematical induction. The principle states, for each natural number n in N, let P of n be a statement about the positive integer n. If P of 1 is true and P of k plus 1 is true whenever P of k is true, then the statement P of n is true for all n in the natural number. In other words, if the statement is true for the particular value of n equals 1, and if the statement is true for some value of n, k plus 1, whenever, if it is true for the n value k, then the statement must be true for all value of natural numbers. The steps A here is called the base case, and the step here, B, is called the induction step. Proof. The proof requires the application of the well-ordering principle. Please see the textbook for the details. Let's have a look at an example. Let P of n be the following statement. So this is the P of n. It's a statement, possibly true or false, but it's a statement involving the natural number n. Now we see that P of 1 is true. Means if we substitute the value of n in the both hand sides, we obtain 1 in the left hand side, and half times 1 times 2, which is true. Now suppose P of k is true. Means this equation is true. We must show that the statement is also true for k plus 1. Means the equation 2 here is true. To prove this, we add k plus 1 to the both hand sides of equation 1. Which we have done it here. then the right hand side can be simply factored and be written in this form, which is exactly the equation 2. This proves that the statement is true for the n value k plus 1 whenever it is true for the n value k. By the principle of mathematical induction, the statement p of n is true for all n. This means this statement is true for all n. Let's look another important example. If h is a real number larger than -1, then this statement is true. It says that the nth power of 1 plus h would be larger or equal to 1 plus n times h. This is known as Bernoulli's inequality, named after Jacob Bernoulli, a prominent German mathematician from the Bernoulli family. There are 7 prominent mathematicians from that family who made important contributions in calculus, analysis, and several other branches of mathematics. Let's have a look at the proof. Let p of n be the statement and see the base case p at 1 is 1 plus h larger or equal to 1 plus h. It is just obtained by substituting the n value 1. Which is clearly true. Now we see the induction step. Let us assume that the statement is true for the n value k. Means equation 1 here is true. We want to show that the statement is also true for the n value k plus 1. Means we want to show that equation 2 is true. To show this, we multiply both sides of equation 1 by 1 plus h. We multiply both sides of the inequality 1 by the quantity 1 plus h. Note that 1 plus h is positive, since h is larger than -1. Therefore, in the left-hand side, we would obtain the k plus first power of 1 plus h, which is larger or equal to the product 1 plus h and 1 plus kh. If we expand the right-hand side only, we would obtain 1 plus k plus 1 times h plus k h squared. Since k h squared is non-negative, so this quantity would be larger or equal to this quantity here. And this is exactly the equation 2. The proof is done. The modified principle of mathematical induction. Sometimes a statement about the integers n need not be true from n equals 1. For example, the statement n factorial is larger than 2 to the n holds true for n larger or equal to 4. Because if we substitute the value of n equals 1 in the statement, we see 1 factorial is larger than 2, which is clearly not true. Similarly, if we substitute n value 2 into the statement, we get 2 factorial is larger than 2 squared, which is also not true. And if we substitute n equals 3 into the statement, we get 3 factorial is larger than 2 cubed. The left-hand side is 6, and the right-hand side is 8. Therefore, this is also not true. But if we substitute n value equals 4, we would get 4 factorial in the left-hand side and 2 to the 4 in the right-hand side. So the left-hand side is 24, which is clearly larger than 16. Now, to prove that the statement holds true for all value of n larger than or equal to 4, we need to use the modified principle of mathematical induction. The principle states, if for each n, the integers, larger or equal to some fixed integer n sub 0, P of n be a statement about the integer n satisfying that P at n sub 0 is true and P at k plus 1 is true whenever Pk is true for k larger than or equal to n sub 0. For example, we can consider here n sub 0 is 4, and we are talking about in statement A that P at 4 is true, and in B, P at k plus 1 is true whenever P at k is true for all k larger than or equal to 4. And the principle says that P sub n is true for all value of n larger or equal to n sub 0. Let's have a look at the example. So we have the statement P of n, which reads n factorial is larger than 2 to the n. So the base case is 4, P at 4, which gives 4 factorial larger than 24. And as we discussed, this is true. The induction step. Suppose P at k is true. Means if we substitute n value k into the statement, we get k factorial larger than 2 to the k. We are assuming that this is true. We are naming it an equation 1. We want to show that P at k plus 1 is also true for the n value k plus 1. We must show that the equation is true for the n value k plus 1. Namely, the k plus 1 factorial is larger than 2 to the k plus 1. To show this, we multiply the both sides of equation 1, namely k factorial larger than 2 to the k, by the quantity k plus 1, which is done here. Now, the right-hand side of this inequality can be put into this form, because since k is larger or equal to 1, as k is a positive integer, then k plus 1 would be larger than or equal to 2, just by adding 1 to both sides. Therefore, if we multiply both sides by 2 to the k, we get this inequality, possibly with an equal sign. So the right hand side is none other than 2 to the k plus 1. Therefore, the k plus 1 times k factorial, which is k plus 1 factorial is larger than 2 to the k plus 1. This proves that the statement holds true for the n value k plus 1. By the modified principle of mathematical induction, this proves that the statement P of n holds true for all value of n larger or equal to 4. This is the end of the proof.